Welcome to another podcast. In this episode, we're going to be taking a look at how to prove the harmonic series is a divergent series. I want to start our discussion, however, with sort of a recap of what we learned from the divergence test. Recall from the divergence test that if you have a sum, so an infinite series here, then what we learned was the limit as k goes to infinity of a sub k equaling 0 is a necessary condition for convergence. Meaning that if the series is going to converge, then we know that the limit of the terms went to 0. But here is the issue. The limit as k goes to infinity of ak being 0 is not sufficient for convergence. And what I mean by that is simply knowing that the terms go to 0 isn't enough to say that the series converges. Now, if the series converges, you know the terms went to 0 because it's a necessary part of convergence, but by itself, knowing the terms go to 0 is not sufficient to conclude that the series converges. And the counterexample to that, so the reason why it's not a sufficient condition is it has a really nice counterexample in that the sum, k goes from 1 to infinity of 1 over k, this series converges to infinity even though the terms of the series converge to 0. Now, how do we prove this? Well, I want to prove this by using something called a proof by contradiction. So I'm introducing you to some nice proof techniques here at the end of the course. We talked about induction in class, but here we want to talk about proof by contradiction. So a proof by contradiction starts off by assuming that something is true. And then you work from that assumption, and if you reach a point in the proof where what you've written can't possibly be true, then you back up to the assumption, and the assumption you made must be false. So here's what we're gonna suppose. We're gonna suppose that the sum of the harmonic series, so remember this is the harmonic series, we're gonna suppose that that sum is equal to h, and that number h is less than infinity. In other words, we're going to assume that the harmonic series converges to the value h. Well, what does h look like? Well, h, according to the sum, would be equal to 1 plus a half, plus a third, plus a fourth, plus a fifth, and this would just keep going. Okay, well, let's make the following adjustment to this. I'm going to replace all of the odd denominator terms with the previous even denominator term. In other words, I'm going to look at 1 plus 1 half, and I'm going to replace 1/3 with 1/4, making 1/3 to 1/4, making that smaller. I'm going to replace 1/5 with 1/6, which would be the next term. Then I'll replace 1/7, which would naturally occur here. I'm going to replace it with 1/8, and so on. Whatever h was, this new series that I've substituted in are now smaller. And so if you take a look at this new series, then a couple of things become apparent. This is equal to 1/2. This is equal to 1/3. This is equal to 1/4, and you can see how that is going to keep going. So what I have here, I have that h is greater than or equal to 1 plus a half plus another half plus a third plus a fourth plus and so on. But that's exactly the same thing as, if I look here at the red pieces, that's exactly the same thing as h. I just have an extra half term. So I just proved that h is greater than or equal to h plus 1/2. So this is a contradiction. This doesn't make sense. And the reason that this doesn't make sense is I started from the assumption that this value, h, existed. So I have to go back and say that this was a false assumption. And so the only thing that I can do to reverse that is I now can say, well, it's a false assumption, so the opposite of this must be true. This sum must be equal to infinity. In other words, I can't find a value h less than infinity for which this works. And so what we're left to conclude is that the harmonic series diverges. And that's going to be an important sort of tool in our tool bag for a lot of different things we're going to be using coming up in this section and in this chapter. Primarily as a means of comparing to other functions or to other series that we know something about. Similar to what we did when we did improper integration and using the comparison test, we're going to do the same thing using comparison series called p-series, but we'll take a look at that in an upcoming video. All right, thank you for watching.